All right, so for this one, unpolarized light passes through a vertical polarizer, then it goes through one that's 30 degrees tilted from the vertical, and then it goes through a horizontal polarizer. So if the original intensity of light is 120 lux, we want to find out the intensity and the orientation of light as it passes through the third, after it passes through the third polarizer. So let's see if you can do that. Go ahead and pause the clip and see if you can think through this logic and work through that. And then when ready to check, we can go ahead and hit play to continue. All right, so that underpolarized light passes through. It's all vertical now. And that light passes through one that's tilted, and therefore it's reduced by half for the first one, right? Then it goes through this one, and we have to determine, how much is lost there. So it's 30 degrees from the vertical, so therefore we end up getting 45 lux left at that point. Then we have a horizontal one. So the trick here is to figure out, okay, what is the angular difference between the two? Well, if this one was 30 degrees from the vertical and now it's horizontal, you got 60 degrees difference. And so it's going to polarize it to a horizontal orientation. The angular difference, again, we've got there from there to there is 60 degrees. And all that's going to be left is 11.25 lux. And then now it's going to be horizontally polarized. So when light reflects off a non-metallic surface, the reflected light is partially polarized, and the plane of polarization is parallel to the reflecting surface. So you can see the light coming from the sun here, and it's unpolarized, and then when it hits the surface, it polarizes, and you can see that most of the horizontal light stays like it is, but the vertical light is, definitely reduced. And so it's horizontally polarized in this picture. So the question we need to ask is, what kind of glasses should we wear to reduce, the light here? And so you can see that, it's naturally polarized horizontally there. So that's what we're going to want to block out. We're going to want glasses that will reduce the amount of light, and so we will want ones that have a vertical transmission axis to block the horizontal light and reduce the overall glare. This is a picture of light that hits the surface, just similar to the last picture that we saw. The light is coming in incident, the light reflects, and some of that light's refracted, right, and then goes into the water. And we need some of that to be able to, be absorbed by the things and reflected off the things inside the water. And that's actually what's going to be more useful for us to see typically. And if you notice here, the small vertical component, right? So the incident light comes in right here, and a lot of that vertical component is cut out. Most of the horizontal stays. And again, some of the light is refracted down there. Here's a couple pictures to see that. If you are wearing vertical polarized sunglasses, you're going to be able to see things more clearly. If you look at this top picture, the light, a lot of that sunlight is hitting and then coming into your eyes. But on the bottom one, a lot of that reflected light is eliminated, and what you're seeing is the light coming from the objects, inside the water itself. Here's another good example here where, the light is up above and it reflects off the surface without a polarizer. It reflects off, but, you got a lot of glare there. With a polarizer, it's much clearer, and you can see, the surface much more in much more detail. Here's another example. I believe this one was a polarized lens that was placed on top of a camera when taking this picture, and you can definitely see the difference between the two. The light reflecting off the grass and off the boy's face here, it makes a big difference. So in this case, it's horizontally polarized. We talked about the glasses that we want to wear. We'd want to wear vertical polarizing sunglasses to eliminate the glare there. And some other uses is kind of interesting in 3D films. You may wonder how do they get that depth, depth information. And what they can do is they can have cameras with that record that have polarizers at different angles, and so it cuts out certain components of that light, and they can get depth information that way, and that can be helpful to create those 3D films. Liquid crystal displays are kind of an interesting thing as well. We talked about earlier, different ways to polarize things. And so with electricity sent through certain types of crystal, it'll polarize the light in certain directions. And so it'll let some of the light through and then some of the light not. And if you have anything, even, most watches look like this, if it's digital, wall clocks, a lot of different things can work that way.